Um, Again, I figured this is going to be big with my AP students, but obviously, if others would like to join, that is fine. I've been doing this every day for the next foreseeable future 4 weeks, 3 weeks, whatever it is. And for AP kiddos tuning in, I know a lot of you guys had questions. What I'm just going to do is I'm just going to go over the whole AP classroom. Let's just do all of it. Let's start from scratch and do all of it. Let's make it easy, avoid the questions, and just start from the top and just go. Okay? But in the meantime, let's wait for a few more people to join before we get started. Chat's open. Remind is also open. Everything's open. Everything's great. We're doing great. Nothing to worry about. Hopefully this won't be as laggy as it was before. I turned off the sharing my screen portion of it, and I'm just focused on. I put all the questions on my iPad. Make it easy. People starting to join in. I'm just going to go over the AP classroom assignment for AP. Region students, if you're joining in, obviously feel free to ask a question. But this does not need to be dominated by the AP students. So feel free to butt in on Remind or in the chat. Hold on. I need to figure out. There we go. That light is just bothering me. Nope, that didn't do it. It's like that light's too bright. It's like shining off my webcam. Did that help? Nope, that's not doing the trick. It's fine. I'm not that important. Peyton, I think it's just me and you right now, just hanging out, you know? Hello, Peyton's brother. I'm guessing your name is Holden. I'll leave the rest of the username in the chat. I don't know what you're gonna get out of this. This being an AP Chemistry dominated review session. Again, I am allowing my Regents kiddos to join in, but I imagine that will be there will be a lack of them. So far, there we go. Now the viewership's starting to go up. So, I'm going to get started in a couple minutes. I'm going to go over the whole AP classroom. The whole thing. So, don't worry about specific questions. Let me charge my computer. Don't worry about specific questions. I'm just going to go over the whole thing. Let's hold off questions until after I've like completed going over a problem. I'll pause and then I'll move on. No, I'm not even close to my PS4, Peyton. Alex, it's up to you. You can, or you can just follow along here. It's whatever. You can see the first question right now. You can have it up while we're doing this, if you'd like. Usually I would say do the AP Classroom first. If you do it while I'm doing it, I have no idea if you get it. And neither do you. You're like, yeah, Mr. G sounds about right. Yeah. So, I'll wait a couple more minutes and I'll get started. Nice. This whole working from home thing makes me want to like totally get rid of my laptop and just get a dedicated desktop with 2 monitors. Peyton, maybe you can help me build it, you know? That could be a great break assignment. Build a PC for Mr. G. All right, I'll give it one more minute. I think most people have started to join in. I'm going over the AP Classroom assignment. No, it's not C. Okay, Peyton. I don't think you're getting that much. I think Mrs. G is being very reasonable when she sent out a bunch of text messages earlier of all the students that have not even logged into Canvas, let alone done their work. All right, 8:05. Seems as good a time as any to get started. Again, I'm going to go over the AP Classroom here. I'm just going to go question by question, pause, and then keep going. I think that'll just wind up being a lot easier than getting a barrage of text. Say, hey, can you just go over number 12? Then I skip to 12. And someone's like, hey, can you go over number 2? I'll skip to 2. Which is fine, and we can do that at the end. But, question 1. So, equilibrium reaction shown above represents the partial ionization of a weak acid, HCN. So, we know it's a weak acid because it tells us. We know it's a weak acid because it has a small K. And we know it's a weak acid because it was not one of the strong acids that we have memorized. So, great news. We know this is a weak acid. If 0.05 grams, and they give you that in moles, of NaCN is added to the solution. So in this question, we just have like a solution of HCN. We're not titrating it with anything. We're not mixing an acid with a base or anything like that. Actually, I can change the size of my marker now. That's way too big. You just have an acid in solution, and you're adding into it NaCN, which is a salt. NaCN is a salt that has an ion in common with our acid, that being the cyanide ion. So what's happening is we're increasing the concentration of cyanide in our solution, which means we have what's called the common ion effect happening. Since NaCN has an ion in common with the acid in question here, the acid being HCN, that is going to mess around with the equilibrium of this reaction and cause a shift. And since cyanide, that I've circled there, is a product in this reaction, increasing the concentration of that will cause an overall shift to the left, which will increase the amount of reactants we are producing. And in doing so, since you're increasing the reactants, the product concentrations will have to go down because products make reactants in reversible reactions. And if the products are going down, one of those products is the hydronium ion, which is H3O+. Hydronium ions measure acidity. If the concentration of hydronium is going down, the level of acidity is also going down. Therefore, the pH will be going up. Another justification you might have given is that the cyanide ion can also react with the water, causing an increase in hydroxide concentration. But that just wasn't an answer choice. You're ending up mixing an acid with its conjugate base here. And for this question in particular, this is just really testing the common ion effect. So nothing wrong in thinking about how a salt on its own could affect what's going on in a chemical or when you mix it with water. But that just wasn't what this question was really asking. That wasn't what this question was testing. And that wasn't an answer choice that we saw. So common ion effect will disrupt the equilibrium. In this instance, the ion in common was a product, which will shift the reaction to the left. And in doing so, it will decrease the concentration of our products, which in this instance decreased the pH. That was number one. I'll hold for a sec while I get number two here set up. If people have a question, you can interrupt. If not, I'll just keep going. Even if I start number two, if you're like, wait, what? Feel free to interrupt. 2. Buffer solution is made up of acetic acid and sodium acetate. So this is a good kind of review of what a buffer is. We have a weak acid, and we have dissolved a salt that contains its conjugate base. In this case, CH3COO- is a conjugate base of acetic acid. So that has created a buffer here. Which of the following equilibrium could be used to support the claim that the addition of a small amount of NaOH to the buffer will result in only a very small change in pH? So we are essentially being asked to prove how we know this is a buffer. And the same thing could have been asked if it was a strong acid being added to solution, let's say HCl. So when NaOH is dissolved in water, you are going to produce sodium ions and hydroxide ions. It is the hydroxide ions we are worried about affecting the pH because hydroxide measures alkalinity or how basic something is. And if that concentration is increasing and we have a buffer here, the buffer needs to do its job and get rid of those hydroxide ions to keep the pH relatively the same. Again, no buffer is 100% perfect. The pH might change a little bit, but we don't want the pH to jump up from 4 to, let's say, 10. Maybe it will jump up from 4 to 4.2. So in the back of our minds, at the very least, we want to start looking at answers that are causing these hydroxide ions to go away. And that will eliminate A and D. C shows that the acid reacting with the hydroxide ion is a hydronium ion, and it's reacting with it to make water. And we do not have that in this case. While that is one of the reactions you see given up here, that is not what is reacting. That is not part of the buffer system. The buffer system is composed of the weak acid and its conjugate base, in this case, CH3COO-. In addition to that, this is showing the kind of auto ionization of water and not showing how a buffer works. So that last one there is kind of like proving KW, which is not what this question is asking about. It is asking about the buffer system we have created, which again is that weak acid mixed with its conjugate base. In this case, the acid, which is acetic acid, will react with the hydroxide ion to produce the acetate ion again in water, helping keep the pH relatively the same. That was 2. 3. Of course, when I print these off of AP Classroom, they never tend to come out looking pretty. And in this case, the table was gigantic and the question was very tiny. The question here was saying, based on the data, which of the following provides the best reason for the trend in base strengths? This is going to be very similar to the trends we learned in acid strengths. So if we look at their structures, they are all identical. We have not added more oxygen atoms or ions into their structures. All we have really changed is what is bonded to the carbon at the end right there. In one case it was H, in one case it was I, and in another case it was Br. So the principle or the concept in play here will be electronegativity. If we look at the answer choices, one of them talked about resonance structures, which in this instance you can show some resonance here. But remember, we are trying to prove base strengths, which you can think of as a reverse of acid strengths. Thanks, Mrs. G. And the principle we'll be concerned with here is going to be electronegativity. Resonance structures are really good to talk about the stability of the conjugate base, which plays a role in acid strength. The number of hydrogen atoms will not play a role. That is not one of the principles we discussed when talking about acid-base strengths. And the different molar masses, again, does not play a role when we discuss the strengths of acids and bases. So this question was a little bit of a throwback to the previous unit, but again, important to make sure we remember. And the only answer choice that really made sense in this case was electronegativities. First three questions down. Okay. I might not pause long enough. Sometimes there's a little bit of a delay on my end to your end. Not that the video and my audio delays, but clearly, like, as I'm talking right now, that's instant. And when you see it, it's a little bit like 5 seconds, 10 seconds later. So again, if you need to stop me in the middle of a question, even though I've moved on, just shoot me a text or type in the chat. All right, a student mixes a strong acid with a strong base. What is the concentration of hydroxide in the resulting solution? So none of the answer choices are perfectly zero. D is really close. So right now in the back of our heads, we know that the base we are reacting is in excess, and that's pretty clear from the fact that we were reacting more of it. So I would say the easiest thing to do would be to get their moles and then subtract them to see how much is in excess. So the moles of the acid, we had 0.1 times 0.04, and then the moles of the base was 0.1 times 0.06. So in one case, we are going to get 0.004, and in the next case, we're going to get 0.006. So obviously our base is in excess. When you subtract the two numbers, you get 0.002 moles of base in excess. The total volume now is 100 milliliters. So I'm going to divide that by 0.1. And that will get you a concentration of 0.02. So when you mix a strong acid and a strong base like this, they will neutralize each other, as acids and bases do. However much is left over is dependent upon their initial concentrations and initial volumes. Get moles to determine who is in excess. And once you have figured out the number of moles, make sure you take into account the new volume since you've mixed them together. In this case, it was 100 mils or 0.1 liters, and we get our new concentration. The acid ionization equilibrium for the weak acid is shown above. We want to prepare a buffer with a pH of 3.5. A student needs to mix 250 mils of 0.1 and 250 mils of 0.1. So He is mixing equal amounts and concentrations of the acid, which is HF, that is a weak acid, with the salt that contains its conjugate base, which is KF. The student accidentally mixes the correct volumes, but half the concentrations. Which of the following is the result of this error? So, we're still going to make a buffer. That is still being created here. We have mixed an acid with a salt that contains its conjugate base. A buffer is being made. The only issue that the kid did was the moles of acid and the moles of our conjugate base are going to be much less than they were before, about half as much, because the student used half the concentrations. And because of that, this is going to affect what is known as the buffer capacity. A buffer will work as well and as long as it has moles of acid and conjugate base to react with any acid or base you add to the solution. So if a buffer is created that has 1 mole of acid and 1 mole of conjugate base in solution, that will have a better capacity than a buffer that has 0.1 moles of acid and 0.1 moles of conjugate base, because the one with 0.1 moles will run out first, and then any excess acid or base that you're adding to this buffer will cause a drastic change in pH. That is buffer capacity. How well is your buffer at maintaining and doing its job? So the correct answer in this case was A. The buffer will have a lower capacity because there is a smaller number of moles available to react with any acid or base added to it. We wanted to make sure we crossed out C because that said it had a higher capacity, and we wanted to cross out D because that said it would have the same capacity. B does correctly state that it will have a lower capacity, but then goes on to state that the smaller amount of HF and F- will lower the pH of the buffer, and buffers of lower pH have lower buffer capacity. That has nothing to do with buffer capacity. Buffer capacity is all about how many moles of acid and the conjugate base, or vice versa. You can make a buffer with a base and its conjugate acid, but it's all about how many moles we have in solution. The more moles, the better. Ideally, you would want them to be relatively high and equal. So a buffer that has 1 mole of acid and then 0.1 moles of conjugate base is not going to do a great job at withstanding changes when you add an acid to it, but will do a better job with base. Either way, it's about moles. All right, number 6. So we have a reaction of a weak base going on here. It gives us a KB, may or may not be important. Which of the following is true about the more concentrated 0.3 molar NH3 and Y? So we have to keep in mind we're talking about the more concentrated NH3 and what would be true about that. So first, if you are a more concentrated base, you should be making more hydroxide ions, and therefore the pOH should be lower than the less concentrated base. So let's start there. pOH should be going down. So if you did this in advance and you think it should have been going up, the pH should be going up. pH is a measurement of hydrogen concentration. pOH is a measurement of hydroxide concentration. In this case, all the answer choices are talking about pOH. pOH won't be higher. pOH will be lower. The lower the pOH, the more hydroxides ions there are. The lower the pH, the more hydrogen ions there are. Just remember, a lot of times on the AP Chem, especially on those free responses, they're going to ask you what is the pH of this solution, and the calculations might involve hydroxide ions, which is fine. You still get the pOH by taking the negative log of the concentration of hydroxides. Just remember that the pH plus the pOH equals 14. So just do a little 14 minus pH to get to the pOH, or 14 minus pOH, my apologies, to get to the pH. that has nothing to do with this question. I just wanted to review that really quickly because that can be a confusing topic. In this case now, we know the pOH is going to go down. We know the hydroxide ion concentration is higher, and all their reasonings are great. We just need to figure out what's the concentration going to be, 3.2 or 2.3. I don't know if there was any reasoning why they would make 3.2 an answer choice other than it has the same numbers and therefore you might get tricked out. The answer is C. It should be the same as the equilibrium concentration as NH4 because they are in a 1-to-1 ratio. I don't know, at least I haven't worked out the problem in a way to mathematically incorrectly get to 3.2. I just think that was put there because it is involving the same numbers. Can't go wrong with Michael Jordan, 2-3. Okay. The equation above represents the acid ionization equilibrium for HF. To prepare a buffer with a pH of around 3.5, 4.2 grams of NaF should be added to 500 mils of 0.1 molar HF. The buffer is accidentally prepared using 90% NaF instead of 99% NaF. Assume that the impurities in the NaF samples are inert. Which of the following explains how the error affects the pH and the capacity of the buffer? Thank you, Hudson. That's true. So Hudson pointed out that the 0.15, just in the previous question, is double to 0.3. So you might accidentally assume that you will double 1.6 as well. And 1.6 doubled is 3.2. So true. Thank you. So that would be the mathematical mistake that could have gotten you to A if you did this in advance. Okay. Anyway, so which of the following explains how the error affects the pH? The end. Okay. Let's read through all of these. First, I think we should rule out any answer choice that says the buffer will have a higher capacity, just based on what we just talked about. Because the student is using 90% pure NaF instead of 99. So the capacity of the buffer should be less because we have less conjugate base in this case. So I'm going to rule out any answer choice that says higher capacity. Then from here, since I have less conjugate base available, that's going to leave me with C. The pH is going to be slightly lower than 3.5 because our acid, in this case, is outnumbering our conjugate base. So that's going to slightly lower our pH. The end. So pH is going to be slightly lower than 3.5 because our acid is now outnumbering our conjugate base based on using the 90% instead of 99. And we know that the buffer will have a lower capacity because, again, we have less conjugate base available. That lowers the ability for the buffer to react with any acid added to it. 8. A student prepares a lactic acid sodium lactate buffer solution by mixing 40 mils of 0.5 with 200 mils of 0.1. The pKa of lactic acid is 3.08. What is the pH of the resulting solution? I went over this one before. So we're going to have a little log conversation. So pH equals pKa plus the log of the concentration of our base, our conjugate base, divided by the concentration of our acid. Our pKa here is 3.08. Based on the amounts we're mixing, I can see that we're adding a big volume of our conjugate base at a very high concentration, double the concentration, I should say, and our acid is at a 0.5 molarity, and we're only adding 40 mils of it. So I know that this, if I were to do the quick mental math here, we're trying to figure out what we're taking the log of. The total volume now is 240 mils. our conjugate base was initially at a concentration of 1 at 200. So I know that 1 is effectively not changing very much. Let's say, I'm going to kind of guesstimate here, maybe it's around 0.9 that it's going to go down. Because going from 200 mils to 240 mils isn't that crazy of a dilution. The other one is going from 0.5 molarity, but the initial volume was 40. Now we've diluted that up to 240. That is 6 times diluted. So the concentration of that 0.5 is going to go down like 6 times. I'm just going to say that's going to be around, it's going to be pretty small. Maybe around 0.1 if I had to guesstimate. You're basically doing the log of 9. And these are totally rough estimates. None of this was good math. I didn't do any math. I'm guesstimating here. I'm basically doing the log of 9. I know the log of 10 is 1. 1 plus 3.08 is 4.08. The log of 9 is going to be pretty darn close to 1. 4.08. Now, according to the key that I read earlier, if you did all the math, you were actually doing the log of 10 in this case. I think just doing a little bit of estimation, just saying to myself, that conjugate base is going to be a lot higher than the acid. I know that I'm going to rule out A and B because there's no way they're the same concentration because they, 1, weren't to begin with, and 2, you're adding a lot bigger volume of conjugate base. And then I'm going to rule out A because the only way you're going to get to A is if it's flipped. So if the acid was at a greater concentration than the conjugate base, that's when you'll start to get numbers possibly going down. Possibly. But I think the easiest way was to do a little guesstimation. Okay? A little tip with logs. So I think that'll come up in the next question. The log of 10, like we just said, is 1. The log of 100 is 2. The log of 1 is 0. I think these are good ones if you're trying to do mental math and you haven't worked with logs before. Sophomores in the room might have just started logs and then we had a week off, or we have weeks off now. This is a good place to start. Log of 1 is 0. Log of 10 is 1. Log of 100 is 2. The log of something that's less than 1 is going to be negative. I'm not saying you need to know what it is, but if you were to say, and we're back in 8, let's say the numbers kind of flip around a little bit, you end up getting it reversed, and you have, 0.1 over 0.9. I know that's less than 1. My pH is going down because it's going to be negative. And I think that's a good place to be. Now you can kind of just like guesstimate. Because a lot of on the multiple choice, they're not like necessarily guaranteeing that you get the calculation exactly right. You can do a little guesstimation, look at the answer choices. You can probably eliminate at least 2, in some cases all 3, just by accurate and good guesstimation. So whoever just texted me, and you know who you are, and I know who you are, about worrying about the mental math, sometimes it's just about eliminating answers effectively. If you need to work on the mental math, that's fine. We can work on tips and tricks the next 3 weeks to just totally do awesome on the mental math. I'll pull Mrs. G in here. We got nothing to do. We're quarantined right now, We're not going out. Let's go in here. Let's do some mental math. Okay, next question's basically the same. We got another buffer, and I'm sorry if this takes longer than an hour, but I think we need it. Did you guys ever take a step back and go, what the heck happened this last week? How many of you remembered there was an earthquake? Hello? We had an earthquake in like the middle of the week, and that got totally overshadowed by all this COVID stuff. Monday, we were a mess because the day after daylight savings, so most of you probably don't even remember Monday because no one was awake. Halfway through the week, earthquake, and then Thursday, Friday, bunch of kids out. There's news going around about schools closing. Are we going to close? And then Saturday, boom, we're closed until after spring break. It's nuts. What a crazy week. Hold on, my computer charger came unplugged. All right, I'm back. So, next problem's basically the same thing. We got a buffer. It's a little bit easier. Because the volumes they gave you were a bit easier to work with. We weren't going from like 40 to 240. Like, what? So, here in this case, we got our pH equals our pKa plus log of conjugate base over acid. Some of you are sitting there right now, all 10 of you watching this going, oh yeah, there was an earthquake this week. Totally forgot. Our acid is the guy here. Our conjugate base is that. And we took acid. So our acid was 100 mils at 0.2. And our conjugate base was 100 mils at 0.1. I'm going to even stop right there. You know, we do all these problems in class and we're going to do all this work. I'm going to stop right there because I know for a fact right now, since you're adding equal volumes, the concentration of them will go down. They're just going to go down proportionally by half because your total volume now is 200. So you're like, oh, I'm going to do the concentration and blah, was it 0.05, 0.5, make a silly... No. Since they're getting diluted the same way, they're each changing the same way, I'm not even going to change their concentrations because it's just one's going to go from 0.1 to 0.05, the other one's going to go from 0.2 to 0.1, and I'm going to divide them. It's going to get the same answer as if I divided the 0.2 and the 0.1 to begin with. All right? That's not going to work every time. You couldn't do that in the previous problem, but if they're starting at the same volume, that means they're getting diluted the same way. I'm not going to worry about doing that math. I'm just going to go in here, and I'm going to say, all right, my conjugate base is 0.1. My acid's 0.2. That's just a half. Who cares about those decimals? That's just the log of a half. That's less than 1. This is going to be negative. The log of something less than 1 is negative. Even if you couldn't figure out that was a half. Doesn't matter. You were doing 0.1. You were doing 1 divided by a number greater than 1. That's going to be less than 1. And the log of something less than 1 is negative, which means I'm going to do 4.8 minus something. Minus something. Get rid of those. Now, I'm not going to do 4.8 minus 3. Okay? If you take out a calculator right now and do the log of 0.5, it's not going to be negative 3. B. Like, I don't get a calculator. Get familiar with logs. Do the log of 0.01. Yeah, I'm getting text now. Oh, yeah, we did have an earthquake. Totally forgot. I know. I almost forgot. And someone reminded me. The log of 0.01 is negative 2. We're still not at 1. 4.8 minus 1 or minus 2 is 2.8. Get familiar with logs. Just take out your calculator and just do the log of random numbers and be like, oh, okay, that's cool. That's neat. 10 I barely even looked at because it's basically the same as 8 and 9, just getting you to set it up. I will tell you that it's C. And the reason it's C is you have to remember that you are adding the volumes together. So your new volume is 15. So A and B are like, I'm not even going to talk about that. And then, no, it's not. We're going to bounce back from this. We're going to bounce back. We're going to be okay. And then, what did the other one mess up on? At least I got the volumes right. I barely looked at this question because it was basically the same as the other two. What did you do wrong here? Let's see, 0.005, okay, times 0.1 plus... Oh, these ones, you're basically like doing the wrong thing here. You're including your acid and your base. That's what it looks like. And you don't want to do that. Because remember, you're doing the conjugate base divided by the acid. You don't want to include both each time. And then you didn't want to add them. That was doubly wrong. All right. But our answer here was C. 11. All right, we went over this one before. Oh, no, we didn't do this one. Oh, this one's easier. This one's a lot easier. So, which one best estimates the pKa of HB? So we're trying to figure out what the pKa of this acid is, or in this case, this base, HB+. So, graph shows a titration curve of weak base with HCl as a titrant. Based on the graph, which best estimates the pKa of HB plus. So, we had to, and the key word here is best estimates. Best estimates. We know the equivalence point was going on right at 50 mils. And we will end up finding that the half equivalence point is right here. Because that's about 25. So that's where the pH equals the pKa. That doesn't look like 10.8 to me, but I'm guessing that is close enough to the right answer. Well, actually, no, never mind. Because I'm not looking at my axes. 11 sandwiched right here in the middle. I'm sorry. So that does estimate it well. I was like, wait a minute. What's up?
Did I leave my cup in here? No.
No.
Okay, never mind.
So that did estimate it well. Mr. G, watch your axes. So 11's in the middle of 10 and 12. I hope you knew that. And it's right in the half equivalence point. So half equivalence point is where we are memorizing pH equals pKa. Heck yeah. Done. And that looks like 10.8 to me. So that looks right. All right, hold on. I got a bunch of texts. So many texts. Okay, we're back. Going down to 12. Oh god. I like these ones for you guys to figure out, but they are a pain to go over because they're so long. Student mixes 100 mils of 0.2 molar CH32NH with 100 mils of 0.2 molar CH3NH2Cl. So we have an acid or a base, and then we have a salt containing the conjugate. Yeah. And the student is wondering, or we're trying to figure out, oh no, the student's claiming something here. We're trying to figure out if the amount of base added to this buffer when the buffer was originally made with 200 mils of 0.2 molar instead of 100 mils of 0.2 molar. We're trying to determine which claim is, well, what did the student claim, Mr. G? Let's start there. The student claims that if a small amount of strong base is added to the mixture, then the resulting change in pH of the mixture will be smaller than the change in pH that will result from adding the same amount of strong base to 200 mils of 0.2 molar. So we've basically changed this number here from 100 to 200. We've added the same amount of base to each buffer, so they're prepared the same way. So let's say the kid added 10 mils of strong base to both of these, 10 mils of 1 molar, to buffer 1, which was made with 100 mils, 0.2 molar of base, and then buffer 2 was made with 200 mils of 0.2 molar of base. We just have to figure out if the kid is correct. So the kid believes that the original buffer will have a smaller change in pH than the buffer with 200 mils of 0.2 molar. So the kid is correct. So we got to kind of like evaluate each of these choices because goodness, they're lengthy. So first, let's read the right answer. The claim is correct because the mixture contains a significant amount of the acid which can react with and partially neutralize the strong base, thereby reducing the change in pH. In 0.2 molar of the base, the concentration of the acid is very small. Therefore, the added strong base is not neutralized and the pH change will be larger. So in the first example, in the first buffer, the student added equal volumes and equal molarities of the acid and its conjugate. In the second case, the student doubled the volume of base he was adding while keeping the volume of the acid the same. So, in the second case, the student would be correct. The concentration of the acid would be smaller because of that doubled volume of base that we've added into the solution. Because we also have to keep in mind that the kid is adding base, so we're most concerned with the acid concentrations. The more acid concentration we have, the more the buffer will be able to withstand that concentration of the base you're adding to it, because it's the acid that needs to neutralize that base. If we doubled the volume of our base and not the volume of our conjugate acid, that is going to throw off our concentrations. That is going to have the amount of acid available be very small, and therefore if we add more base to it, in this instance a strong base, the pH is going to have a more drastic change. A was wrong. Let's see. The claim is correct because the mixture contains only half the CH3,2NH that the 0.2 molar contains. The lesser amount of base in the mixture makes the pH of the mixture lower than the pH of 0.2 molar. Therefore, when a small amount of strong base is added, the pH change will be smaller. So A just like totally ignored the acid entirely and just kept talking about the base. It was like base, 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 base. Not the reasoning we want to be talking about. And I think pretty much every other answer choice just failed to understand what the buffer's doing. If you're adding a strong base to the buffer, you want the acid to be available to react with that base. I don't think any of the other answer choices really just like got to that point, making B the best one. All right, this one we did before. So we had to best estimate the concentration of the solution of the weak base. So we have 25 mils of base of unknown concentration. We are adding to it 0.1 moles of acid. When you get to the equivalence point, which is going to be right here, it's that part of the curve where it like, let's review these curves real quick. We got like buffer zone, buffer zone, buffer zone. At some point, you'll get to that point where the moles of acid and the moles of base are the same. And then as soon as you add a little bit more acid, your pH is going to drop significantly. So we hit that equivalence point right here at 50 mils. And right here we know the moles of our acid equal the moles of our base. Right at that 50 mils point. So we have added 50 mils of acid. So I'm going to do 0.1 times 0.05. Convert that 50 mils to liters to get 0.005 moles. We know that will be the same as our base. So from here, we know that our base is also 0.005 moles. If we divide that by the initial volume of our base, you're basically doing 5 out of 25, which is a fifth. So, mental math. I hate decimals. If I multiply these both by 1,000, you'll have 5 divided by 25, which is 1 over 5. You know 1 over 4 is 0.25 because that's a quarter. 0.2. So remember, it just said best estimates here. Best estimates. That's a not perfect, but a decent estimation. We know at the equivalence point the moles of acid and base are going to be the same. At the equivalence point, I added 50 mils of acid. I know the concentration of acid. Therefore, I can get moles of the acid, which means I can get moles of the base, which means I can get concentration about initially. Mental math tip. Sometimes you're dealing with fractions with decimals. What I like to do is just multiply the numerator and denominator by the same number until they become easier to work with. Multiply them by 10, 100, 1,000, something that gets rid of that decimal that is so painful to look at, and do 5 over 25. Oh, okay. I can reduce that to a fifth, and I can figure out what that is. All right. Based on the data, which of the following species has the highest concentration in an aqueous solution of glycine with a pH of 7? So, we have a reaction here where we're getting a kind of like two curves. We're getting a big change right here and then like a little one right there. We're trying to figure out which one is going to be highest when the pH is 7, which is right here. So we have reached the first equivalence point. So we're mainly concerned with this reaction because that's the first one. And then that guy is the one we're worried about when we get to here. But the question's not really having us concerned with looking at that second point. The question's just having us look at that first point, because that's what the question said, like what's going on at the pH of 7. And at the pH of 7, we've hit that first equivalence point, which means the concentration of that guy is pretty much going to start to go away. And the concentration of this guy is going to be going up. So, I know it can't be him. And remember, it's asking about concentration. So as this reactant is going away, the other one's appearing. I gotta erase all this because now I can't see. And I know it's not going to be the last two because those are more concerned with that second point. And that second point was at like a pH of 11-ish. So I know that you hit that pH of 7 right there, which is like in the middle of that transition out of the first reaction, meaning the product there of that first reaction is going to be greatest. I think this was not as confusing as it could have been. I think it looked more confusing, I should say, than it actually was. All right, 15. Ooh, these buffers. You can see why this unit is so exhausting. Some of these questions are just like so long. All right, a student wants to prepare a buffer with a pH of 4.76 and 25 mils of 0.3 molar acid with 75 mils of 0.1 molar conjugate base. So it's a salt that contains the conjugate base. While preparing the buffer, the student incorrectly measures the volume of the conjugate base, so that the actual volume used is 76 instead of 75. Okay. Not a huge difference. So we're not talking about like completely ruining the ability of the buffer. However, 1 mil, when you're dealing with microscopic things, really sub-microscopic things, will make a big difference. And you'll, not a big difference, will make a difference. That will be noticeable. So if you think about the lab we did at the beginning of the week, we made a buffer, and you notice that some of you were relatively close together. You were aiming to get like a pH of 5, and like some of you get a pH of 6, and you relatively felt like you had good techniques. You were using volumetric flasks. Even if you just said it was close enough, like there's that line on that volumetric flask that says this is 100, and if you were like, that's close enough, that's enough to make a noticeable, not substantial, but clearly if you were to compare it to other groups that were a little more precise, you will see a difference. So in this case, it's going to have a slightly higher capacity for acids because we've added a slightly bigger volume of conjugate base. So when you add an acid to this buffer, you have a little bit extra conjugate base in there, to help you withstand the change in pH if you were to add a little bit of acid. So, not too crazy of a problem. I know it could not have been C, because C said bases. B, the pH of the buffer would be slightly lower because the amount of conjugate base added was higher. I think if you think about that pH equals pKa equation and think about what we talked about before, that's going to be the log of a number bigger than 1, which means we'll have a pH bigger than the pKa because it'll be pKa plus a positive number. The pH of the buffer will be slightly lower than 4.76 because the total volume of the buffer is 101 instead of 100. No, you got to think of this equation again. That's the buffer equation. And volume is important in helping you get concentration, but it says your acid was diluted, which means your concentration of acid is going down, which means you're taking the log of something that's probably going to be bigger than 1. Okay. That is most of the buffer stuff. I think the rest of this is KSP. I apologize for the lack of questions involving comparing K and Q. Watch the video I posted on Canvas for that. I'm going to stop for a minute and say questions on buffers, go, if any. Okay. I'm gonna. Are you going to add back that buffers AP classroom? Are you talking about the videos? I re-uploaded every video about this unit. Anything about buffers, titrations, and KSP, I put those back up, and they're working again. And I had a student check for me, and they confirmed that that's true. Is that what you were referring the originally? I didn't change anything on AP Classroom involving buffers. No longer there. Did I assign something and then get rid of it? I don't think I did. I don't know. I don't remember. I don't remember. I don't know what you're talking about. It's been a long week. I don't know. The original AP classroom before the COVID stuff. Not sure. Not sure. But this was, this was what I was originally going to plan. Did you start something on AP Classroom and then it went away? Because I think I locked like the acids and bases stuff, but not the buffer stuff. Oh, no. I hadn't even gotten around to assigning it because I moved the test and I had a hunch that something was going to happen. So I wanted to wait and see what happened before you guys went hard on doing the AP classroom, and then, stuff happened. So no, I didn't assign it yet. I had something made. I had this ready to go. I just didn't assign it because I wanted to hold off on it. No, you're not. Don't say that. Okay, so let me see. So, someone was just asking about capacity, and let me just kind of summarize it here. So, a buffer is typically going to be one of the following: a mixture of a weak acid and its conjugate base, a mixture of a weak base and its conjugate acid, or you partially neutralize a strong acid and a strong base. Partial neutral. Meaning, if you 100% neutralize it, you have equal moles of acid and base, then all you have left is a neutral salt that's not helpful. So you want to partially neutralize it. In each scenario, the more moles I have of each thing, the better it will be at reacting to what's added to it. So, meaning, in scenario 1, if I have 1 mole of weak acid and 1 mole of conjugate base, if I were to add a base to beaker 1, the weak acid will do a great job at reacting with that base. And if I were to add an acid to beaker 1, the conjugate base will do a great job reacting with that acid. It will do a better job than, let's say, the same buffer, but with 0.1 moles of each. I would say the red buffer, the moles in red, have a higher capacity than the moles in blue because I have more moles of stuff in my buffer. Therefore, it can react with any acid or base I add to it. Just keep in mind that the weak acid in the buffer will help you if you add base to it, and the conjugate base in the buffer will help you when you add acid to it. You get into trouble if those moles are not equal, meaning a lot of the buffers that you guys self-created, just to keep the math simple, you stuck with 0.1 of whatever, and you just adjusted the conjugate you were adding to match 0.1 of the weak acid or base. So if you were to make a third scenario in beaker 1 that was 0.1 of your weak acid and 1 of your conjugate base, that buffer has a higher capacity to react with acids because you have a whole lot of conjugate base compared to the weak acid in the solution. So when you make a buffer, you want to keep in mind that it's a combination of an acid/base with its conjugate. The acid in the solution reacts with base that you're adding to it. The base in solution will react with acid that you're adding to it. The higher the moles of each, the higher the capacity of the buffer. If the moles are not equal, whichever moles is greater, the buffer has a higher capacity to withstand that change. So, the higher moles here was the conjugate base, so this buffer will do a great job reacting with acids and not so great reacting with bases. Versus in scenario 2, maybe I had 0.1 mole of conjugate base and 1 mole, of weak base, and 1 mole of conjugate acid. So, buffer 2 over here has a higher capacity to react with bases because I have a whole lot of acid in solution to react with that base. Does that make sense? So, capacity of a buffer is all about how many moles of acid and base do I have in my solution. If I add base to my buffer, the acid reacts with it. If I add acid to my buffer, the base reacts with it. The higher the moles, the better the job the buffer will do. If they're not equal moles, whichever one is higher, the buffer will do a better job for that one. Okay. It's confusing. It's a lot. Okay, let's wrap this up. Thank you guys for just like tuning in. This is approached the hour mark, and people are still here, and that's great. That's great. 16. Aqueous solution of CDF2 is prepared. In the solution, we have 0.0585 molar CD2 plus and 0.117. You should notice that this concentration is just 2 times that concentration. Excuse me. Because they're in a 2-to-1 ratio in the balanced equation given. Some 0.9 molar NaF is added to the solution. Which of the following identifies the molar solubility in pure water and explains the effect that adding NaF will have? So, we're approaching common ion again. We have added a salt that contains an ion in common with the thing that we are dissolving in solution. So, first, let's do the easy part. What's the molar solubility of CDF2? Basically, that's a fancy way of saying, what's the molarity of CDF2? Not what is the KSP. So KSP is the solubility product constant, and that's equal to the concentrations of your ions multiplied together. So KSP would be the concentration of CD times the concentration of F squared. And that gives you a relative gauge as to how soluble CDF2 is, because if the K is really small, then CDF2 is not very soluble. It does not tell you the molarity of CDF2. And in this case, the molarity has to be 0.0585 because CDF2 and CD2 plus are in a 1-to-1 ratio. So that makes that a bit easier. However, adding F minus CD2 plus 2F minus, we are now increasing the amount of fluoride ions in solution, which brings us all the way back to question 1. We have increased the products. Le Chatelier kicks in. We shift to the left. We are now increasing the amount of CDF2 we have, which means this is now less soluble than it was before because less of it is dissolving. A. Whew. Okay. This is 17. All right. This is like a kind of conceptual thing. The equilibrium constants for the dissolution of various substances is listed above. Which of the following provides a correct comparison of the molar solubilities of some of these substances based on their KSP? So, generally speaking, the higher the KSP, actually this is just true, the higher the molar solubility. KSP and molar solubility are not the same. But KSP gives you somewhat of an idea of how soluble something is, and therefore how big the molar solubility is. So, if we were to look here, the nickel carbonate would be have the highest molar solubility because it has the highest K value when compared to the rest of the substances. Now, CuCN is breaking up into two ions. Cu. I'm going to zoom out. Cu and Cn. Nickel carbonate's breaking up into nickel and carbonate. But MgF2 and SnOH2 are breaking up into a positive ion and two negative ions. So their KSP would be X times X 2X quantity squared, which is why this is 4s cubed and this is 4s cubed, because X times 2X times 2X is 4X cubed. So the right answer here is going to end up being B. The molar solubility for CuCN and nickel carbonate are calculated using S equals the square root of K, which is true because you can just rearrange this expression. And CuCN has a lower molar solubility than nickel carbonate, which is also true because it has a much lower K value. All right, 18. Value of KSP is 2 times 10 to the negative 8. The student places the same mass into 50 mils, measures a bunch of data, blah, blah, blah. Based on the data in the table, what can be concluded about the molar solubility of AgOH? Okay, so as the pH is going up, the molar solubility is going down. Because the K value, well, that's just straight up concentration. So I need to find an answer choice that best explains why, as the pH is going up, the solubility or the concentration of the silver ion is getting so much smaller. Well, when I look at this reaction, I am producing Ag ions and hydroxide ions. If I'm adding a base, the pH is going to go up, which means the concentration of my hydroxide ions is going up. And via Le Chatelier, this is going to shift to the left, decrease the amount of silver ions I have, and increase the concentration of AgOH. If I increase AgOH, less of it's dissolving, which means it's less soluble, which will lead us to answer choice D. So, since the pH was going up, I know I'm getting a big increase in hydroxide ion concentration. That means, based on this reaction that I have here, as silver hydroxide is dissolving, I am increasing my concentration of hydroxides, I am increasing a product, I'm going to shift this reaction to the left, decrease the concentrations of my products, increase the concentration of my reactant, B. I don't know if my snaps are coming through, but they are that one wasn't that good. They've been pretty good tonight. I'm feeling pretty proud about my snaps. All right. Almost done. And then I think I need to call a night because this is taking a lot longer than I thought, which is fine. I don't mind. But I got to make sure to send the video out to you guys. Tips for tomorrow when you get your next AP Classroom test assignment. Thank you. You can rewatch this video again. You can watch any and all of the videos. You can do that AP Classroom assignment at the end of the day. There's no time limit on it. Just make sure you have the Lockdown browser installed. People have noticed that if you did it on an iPad, don't plan on using that iPad for the next few hours. I think it locks you to the one app only for 5 hours. At least that's what happened to a student. That's it. So you can do anything and everything beforehand. Obviously, I want you to just try it on your own to just see how we're doing. I cannot simulate testing conditions when we're not in the room together. There's no time limit on it. If you want to self-pace and you want to time yourself, I highly encourage it. I'm not forcing you to do so. I think we have taken more than enough tests that if you have not gotten used to the pacing by now, you have some serious work to do. So let's just concentrate on learning the material and going over the material once we've completed it, okay? Try to make it as least pressure as possible. All right. The KSP value in pure water was experimentally determined and to be much less soluble when you added NaBr. Okay, how many of these questions am I going to add? NaBr has an ion in common with the reaction above. That's going to go up. It's going to shift to the left. Blah, 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 blah. Pick the answer choice that's best explains that. They kind of got you a little bit with the answer choices, though, let's be honest. The answer was D. The presence of additional Br ions already in the solution means equilibrium will be reached when much less COBr is dissolved. So, it's the same idea. It is just wording it a bit differently. So, it's going to allow us to reach equilibrium a lot more quickly and with a lot less CuBr dissolved, because there's already that ion in solution, so CuBr does not need to split as much as it needed to before. They tricked you a little bit here. Is the test on AP Classroom tomorrow graded? So technically, since this is not like review, that's a lie. Technically, since this is not new material, this is review, I can grade it in some capacity. I don't know how yet. Like I said, third quarter for me right now in terms of what's in School Tool is on a big pause. Because I don't know how to best approach it. So someone right now just asked me about labs and test corrections. I would appreciate it if you got it done. I'm happy you're staying on top of it. However, submissions and all of that, I'm going to pause. I don't want to say... Well, you'll have plenty of time. You'll have plenty of time. If you want to work on test corrections and labs and anything that's currently part of third quarter, feel free. I don't know what the decision is going to be about grades. I honestly don't know. And I don't want to give you an answer. So I will say tomorrow, technically, this is not review. I said it again. Technically, this is review, not new material, so I can grade it in some capacity. At the end of the day, it's not testing conditions. I wouldn't be too stressed out about it. I would just approach it and say to yourself, I'm going to try this on my own. I'm going to do the best I can. And I know Mr. G is going to go over it with me at some point. So labs, test corrections. I'd love if you did your test corrections. Let's prioritize those. Your AP exam is coming in some way, shape, or form. If we can get those done, that would be amazing. I don't know how I'm going to handle the grading thing because it's just... I have a lot of students that missed labs, and I have students that maybe not necessarily in our class, but in my Regents classes that missed tests, and I can't fairly give them a test, and I don't know what I'm going to do about it. No, you may not come and drop stuff off in my mailbox. You may drop it off at school, but...
No, they can take a picture and send it.
Yes, I know, but that's what I'm concluding with, Mrs. G. Don't drop off anything. I'm not giving you my address, obviously. We will have something on Canvas. I will put something on Canvas for you to submit work. But for now, just hold on to it until I get a firm answer on what we think is best. So I even talked to Mrs. Bell about it. I just want to concentrate on this stuff. I want to concentrate on the new stuff next week. I am very confident we will have an abundance of time for all that other work to go in. So work on your corrections. I'll just say that. Let's just keep doing chem. Work on your corrections. And then labs and stuff we'll figure out. And we'll figure out the whole grading thing as the days go by. This is only day 2, people. Right? It's March 17th. I'm getting texts from kids about penguins. What's going to happen in a month? What are these text messages I'm going to get? I sent an article to a student. I should just send it to everyone. Some lady thought the cheese She thought cheese she was using to wash her hands was soap. How do you not notice it's cheese? It smells. It doesn't bubble. What is happening? Oh, man. Anyway. Okay, in this case, you'll notice that as you add more acid, the molar solubility is going up. So, that was easy. As you add more acid, the molar solubility is going up. Nothing here to unpack. Oh my god, am I almost done? Okay, good. Woo! 21. Okay, this gets back at how you set up this expression. So KSP is going to be 2x raised to the power of its coefficient times x. Where'd those x's come from? If you do a quick ice table, the silver would be plus 2x, the carbonate would be plus x, so that's where the 2x comes from, that's where the x comes from. The square comes from the fact that when at the end of the day, you got to raise it to the power of the coefficient when you're setting up these k's. So k would end up equaling 4x cubed, which if you rearrange will get you to d. Dissolution of calcium fluoride is represented by the system above. Fluoride ions is produced when the weak acid dissociates. If solid calcium fluoride is added to equal volumes of the following solutions at 25 degrees, in which solution will the most calcium fluoride dissolve? So we're trying to get calcium fluoride to split. If you were to add it to the solution with acid, so this acid is a strong acid, so in solution it totally splits, you're going to have those hydrogen ions hanging around, which means that those fluoride ions can react with it to form HF, which means we're going to see a decrease in the concentrations of our products. So Le Chatelier says we're going to shift to the right, try to get this to split up more to make up for the difference. That's the end. Woo! This had to be the longest one, but I'm happy to help. Wish I could see all your bright and awesome faces, but I can't. I apologize for that. You're just stuck looking at me for the next 4 weeks or so. I'm going to end it here. I'm going to post it on YouTube. I'm going to send a text message out to all of you right now just saying, take your time tomorrow. No stress. We're going to be okay. If any other questions pop up in the meantime, feel free to text me. Have a good night.